We're going to be doing a little bit of analysis of what the mathematical establishment does. We're going to find out that not a single explanation, physical interpretation coming out of, Harvard, Cambridge, Oxford, Caltech, you name it, they are all irrational. Not one of them meets even the minimum criteria for rationality. So let's start here. We're going to start with a little history here. Let me very brief history of how science, or you could call it physics, developed. Many people equate physics with science. Okay, and here we have a little map and shows you what happened over the last 5,000 years. About 3,000 years BC, we had three regions, maybe Mesopotamia first, and followed by Egypt, and then maybe India around the same time. We don't have exact dates, but around 3,000, maybe even up to 4,000 years ago, you had these regions where they started doing measurements and creating some kind of quantification system in one way or another. I didn't include China because there's not that much information for China. The farthest I could go with 1,000 or like 1100 BC. I'm sure there's more out there, but the point here is that maybe 3,000 years BC, that's when we started measuring the land, and that's when geometry came into being. And geometry is the first step in uniting math with phys, right? We have mathematical physics because you have the physical part, which is the object, the solid, and you have the math part, which is the measurement and the relation of how big something is with respect to something else. So that's where it started, more or less. About 800 BC, the center of the world, of the scientific world, moved to Greece, and obviously the Ionian Islands and some of their colonies there in that whole region of around Greece. And 1,600 years later, about 800 AD, we start with the Ottoman Empire, what they did was they took some of the stuff from the Greeks and they developed it a little further. A lot of it was just technology that they developed, but they developed some new concepts and so on. And eventually we reach Europe first, really around the 1500s, you have Italy and Spain, and then around the 1600s where they made most of the advances or the changes. We have this scientific revolution, primarily in France, Germany, and England. Okay, so that's more or less how science moved over the centuries. Okay, so from there you can say that we ended up in the 19th century, again, primarily in Europe, with people developing notions of what light is, specifically electromagnetism. They discovered electricity. They played around with magnets, tried to figure out what this thingy called field is. And eventually we stopped doing what is known as classical physics, classical mechanics, and we ended up with the nonsense we have today, which is quantum mechanics and general relativity, followed by bigger nonsense still, which is string theory. So all we have today is nonsense. And we're going to see that is the case, exactly like that. Okay, so what is nonsense? What is irrationality? Let's start there so we have a definition we can all sink our teeth into. Here it is. Irrational is deprived of reason, and reason is a basis or cause. That's according to the dictionary, okay? And I mean, that's not very clear, but you get an idea of what we, in general, what we mean by irrationality. But we like to define it a little more specific for physics, okay, science. If you attempt to move a concept, your theory is irrational. We cannot move concepts, okay? You can only move objects. So all those people who talk about the ether, field, plasma, energy, mass, time, you can't move those things because they are not things, okay? And so anyone trying to move or in any way modify, vibrate, bend, etc., any of those concepts, that's irrational. That's an irrational theory, because you should be able to use words such as bend and move and orbit or whatever. You should be able to apply it only to objects. That's starting point. You can't. That's non-negotiable. Then you have inconsistent definitions. First of all, people don't define. Nobody has learned how to define words scientifically in the last 10,000 years. So we don't have scientific definitions, and we do harp on scientific definitions here, because if you're going to communicate ideas, we need to know precisely what you're saying. Otherwise, different people interpret different things, and we're all lost. We're debating in circles. This guy thinks this and says that, and the other guy thinks something else and comes, with a wrong answer to the wrong question, and so on. Now, you need to have definitions. They have to be consistent. If they're consistent, they're rational. If they're used consistently, they're rational. They're scientific. If they can't be used consistently, like the words energy or mass, there's 7 definitions for mass. Field, we don't know what a field is. It's defined as a bunch of numbers, and they start saying we're going to vibrate them. You can't do that in physics, not in science. Okay, so that stuff does not belong in science. That language does not belong in science. And then you have unimaginable objects, mechanisms. They have this object called 4-dimensional space-time, and they say we cannot imagine it. Okay, so what am I supposed to be imagining, visualizing when you talk about space-time? And space-time's the easy one. They talk about 10-dimensional objects, 11-dimensional objects, 26-dimensional objects in string theory, and that's beyond any hope. Okay, so no, there's only 3 dimensions. It's length, width, and height. Those are the only ones we can conceptualize having direction at 90 degrees to other directions. Period. We're done. That's it. Anything beyond that is irrational. So anyone who talks about 4D and above, or less than 2D, they talk about 1-dimensional objects, 0-dimensional objects. No, I cannot imagine that, really. I'm not that smart, okay? And then the theory doesn't follow from the assumptions. And I use a very simple example. The prosecutor presents a knife at the beginning of his case, presenting his case, and then talks about, the person being shot or poisoned or whatever. No, it's got to follow from the assumptions. If you're going to make the assumption that the murder weapon was a knife, hopefully the theory says something about stabbing, okay, that sort of thing, okay? And so we have to be consistent in other the theory has to follow from the assumptions. So all these are what we call irrational. Anyone that doesn't follow those guidelines is proposing an irrational theory. That's the way we look at it. Okay, so here we have some strategic irrationalities that plague what we call mainstream mathematical physics, right? And here you have a listing of them. The definition of object. No one has ever defined what the word object means. And they do have some definitions out there, but they're all irrational. They talk about the see-touch criteria, that you have to see an object, you have to touch an object, and those two are irrational. Why are they irrational? Because in order to see, you need another object. In order to touch, you need a second object. In other words, to define the word object, you're invoking already another object. You're invoking 2 objects. They have to touch each other. The asteroid has to hit the moon for both of them to become objects, meaning that before they touched each other, they were not objects. An asteroid standing all alone in the universe, that's not an object according to these definitions. And then, there's another one which says that an object is what it's made of, made of a bunch of objects. No, that's also irrational, because you can't say an object is what is made of many objects, okay? And they say, use that for the particle, especially definition. Then you have the definition of exist. Why are these 2 definitions important? Why? Because physics is a discipline that cannot be done without objects. You need objects to do physics. If God comes in there and wipes all objects from the universe, you have absolutely nothing. What is happening? what is taking place. What are you seeing? What are you measuring? What are you analyzing? So this is the issue. And then you have the definition of exist, the same. Exist is the in other words, physics is the science of existence. Okay, if you do not define the word exist, you do not have any physics. That's how simple it is. Physics is the science of existence. Physics tries to elucidate what exists out there, especially those invisible, intangible objects, right? And with them, try to explain how the universe works. So you do absolutely need the word object and the word exist. One of the reasons theists, atheists, and agnostics go around in circles is that they never define the word exist. And they say, well, yeah, let me look at the dictionary. And that's the worst place to find a scientific definition. You will not find a single definition in any dictionary on planet Earth. Okay, so don't look it up because it's going to be irrational. Why is exist irrational? Because they're using synonyms. They're saying, well, it's to be, or living, or reality, or what's real. And you look up those words and they say they're defined on the basis of exist. So no, exist you cannot define, or object you cannot define on the basis of synonyms or antonyms. You can say an object is what it's not. That's not a definition. That's a synonym, an antonym turned into a synonym, right? That's what it is. Okay, ether as an assumption. That's been a plague throughout thousands of years now. No, we do not use the ether. Ether is a bunch of particles. That's all it is. It's this unknown out there, a bunch of particles that form some kind of background, okay? And some of them have it waving, some of them have it vibrating, others want to make it stand still. Others equate it with space, say space and ether are the same things. Others say that space is like a container and ether fills it, and there's no place in space that's not filled by the ether. And they have all these different notions because no one has defined the ether. And so we get rid of the ether totally because it's a word that only confuses, that muddles the conversation. We don't use the word ether. Ether is what space-time is. Ether is what the false vacuum of quantum mechanics is. All of them are ethers. That's why we get rid of all of them, because it's a bunch of particles. That's all ether means. And when people say, no, Bill, you got it wrong, you don't know what ether is. Okay, tell me what it is. In fact, don't tell me. I don't want you to tell me what the ether is. Because if you define it, it's a concept. And you're not going to tell me that you're going to move a concept later on, because now you're doing it in irrationality. You have to point to it. Okay, that's the ether. You got to show me some kind of image. Okay, so you can point to an image, I don't know, in Google or some site that's out there, or your own. I mean, just show me a picture of your ether. Then we can use it as an object, as a thing. Otherwise, it's a concept, and concepts do not move. You cannot use them as a thing that serves for your theory, like you're going to be shaking the ether, vibrating the ether, moving it from here to there. So ether has been a plague throughout centuries, and again, space-time is ether. False vacuum that used in quantum mechanics and all these vacuums that they have out there with different levels of vacuum, they're all ethers because they don't know what they're talking about. Vacuum is not a thing. You cannot say the vacuum does this, like shoots a virtual particle into the real world. That's all nonsense. You have to start by showing me your vacuum first, then, if you're going to talk about particles coming in from the vacuum. Okay? In other words, creating something out of nothing. Similar to that, space has been treated as a thing for the last 10,000 years by at least, I would say, 90% of the people out there. No, space is the opposite of things. Space is nothing. Nothing. Absolutely nothing. What is nothing? That which has no shape. If an object is that which has shape, nothing is that which doesn't have shape. So we have something and nothing. They are antonyms. Now we can use them consistently. We can talk about somethings and nothings, okay? And again, the fact that you use it as a noun in an ordinary sentence doesn't make the word space a thing, okay? It's a noun, it's the subject of the sentence, but it's not a thing. Okay, the other problem, again, mathematical physics is totally irrational because it uses concepts as mediators. That's the big problem. Field, plasma, ether, time, mass, none of those, energy, none of those are things. You cannot use them as things. And they've gotten so used to these words that they introduce them into their physical interpretations. And you cannot do that. Not if you're going to explain a mechanism. You need to have a thing, and none of those words qualify as things. They are all concepts. Concepts cannot be used as objects. He who does use them in their dissertation is doing irrationality. Creationism. Everybody thinks that there's been a beginning and there's probably going to be an end. And that comes all the way to the days of biblical days and even before then. Everybody thought the universe had some kind of beginning. And of course, you needed the guy with a magic wand, and that was God. So he created the universe from absolutely nothing. No, creationism never happened. There is no origin to the universe. There will be no end to the universe as mathematical physics holds today. There was no starting point, no ending point. Okay? There's a single thread in all of space. That's the proposal here. And that turns into every atom and the interconnections that bind them all. And that's been there forever and will be there forever when we're gone. Big problem in mathematical physics, every cosmic phenomenon is done with mass, gravity. It's all gravity. There's nothing else. That's all they touch upon. Mass and gravity and mass. And so what is dark matter? Well, it's some kind of mass energy. What is what is a black hole? Mass energy. That's what they talk about. And no, you can't do everything with mass. There's something else called electromagnetism, right? Another type of, we'll call it force, right, out there. And they don't use that at all. That's the funny part. They don't use electromagnetism at all. Okay, so that's the introduction. Let's see what we have for each one of the branches. We're only going to touch today upon quantum mechanics and later on general relativity. So here's a rundown of what we're going to be covering in quantum, the hypotheses and theories which are irrational. An object, see, touch, again, that's irrational. An object that is what it is made of, right? Those two definitions are irrational. You cannot use those in science. So those are the ones that people use today, primarily the first one there. And of course, if you take like the black hole, you can't see or touch it, and it's not made of anything because it crushed all matter out of existence. So it doesn't meet either one of those two definitions. It's still considered an object. They talk about it being an object. And sometimes they even put the adjective in front of it. It's a mathematical object, whatever that is. I don't know what a mathematical object is. Okay, so we have first this particle is not a particle. That's a big one today. They talk about particle accelerators, particle physicists. They accelerate particles. What is a particle? And when you look it up, this is a big one here, okay? Because this is what it says. Particle or corpuscle in older texts, obviously wrong because a corpuscle is not the particle of quantum, by the way, is a small object. That's how it's defined. Small object. And you look up object and it says it's a collection of matter. What is matter? A bunch of objects. So we have, what is an object? A collection of objects. That's the definition they have. It says which can be described. They're going to describe it. They're going to describe it. They're not going to define. They're going to describe it by several physical or chemical properties such as volume, density, or mass. So they're talking about mathematical concepts. Volume, density, and mass have nothing to do with what an object is. Okay, so the fact that you can describe it or not through these mathematical concepts is irrelevant. We don't care about that. Okay, it says the term particle is usually applied differently to three classes of sizes. So now it's a question of how many sizes they have. In fact, it says before that the term particle is rather general in meaning and is refined as needed by various scientific fields. So everybody has a different definition of what an object is, of what a thing is, okay? And that already gives you an idea we have a problem. It's like they have all these different notions of what an object is, and take whichever one you want. So I don't know, if you're in medicine and you think an object is this, the guy's talking physics and you're thinking of your specialty, your discipline, saying, oh, I know what he's talking about, when you absolutely don't know what he's talking about. He's referring to a word such as object, and you have a different notion what an object is. He's got another one. You're not communicating, period. It's just that simple. And again, says the term particle is usually applied to different classes of sizes. And you have the macro, essentially. There's a couple subheadings there, but we have the macro world, anything above an atom. Okay, so those are objects that usually we can see or touch. Not totally true. You can't see the air. Okay, and certainly you cannot touch the table on the other side of the earth. Right now you can't touch it. So is the table not an object until you touch it, until you go to China and touch the table the China man has over there? So we got a problem with that definition, that notion. Then you have the subatomic world, anything under the atom, and eventually you reach what is known as the point particle, and that's the killer one, and which says it lacks spatial extension. So we have a point particle is that which lacks spatial extension, and what they do, that's the one they're going to use in quantum mechanics, that last one, the point particle. So everything's a point particle. Electron is a point particle, muon is a point particle. They're all point particles. And the funny part about that is they're all also elementary particles. They're fundamental particles. What's an elementary or fundamental particle? One that is not made of other parts, of simpler parts, that has constituents. And they take the pion, they say, what's made out of muons? And both of them are elementary particles. What's a muon made of? It's made out of electron, because once you break it up, you end up with an electron and some other garbage out there, some residue. And so how can they all be elementary particles if one is made of the other? So they have all these contradictions. They just plow over them. They don't care. They don't even pay attention to their definitions. And that's the big problem, because then you don't know what they're talking about eventually. Okay, the next one is that they have this irrationality in quantum that a particle can be at two places at once. I want you to think about that for a second, okay? Does that make any sense to you right off the bat, intuitively? I mean, a particle being at two places at once. It's like, your cat is at two places at once. Is that possible? How can a particle be at two places at once? What sense does that make? If two particles are at the same place, we might be able to think about it. You're seeing a single particle and you're saying it has two different states. That's the way they put it. Okay, fine. That's stretching the imagination. But a particle being at two places at once, two locations, please try to translate for me that one. I don't understand it at all. And you say, Bill, you're pulling stuff out of nowhere. No, here, I'm going to put some authority here, okay? So you see it. This is on Science, right, the magazine. One of quantum physics' greatest paradoxes may have lost its leading explanation. It says, it's one of the oldest tenets of quantum theory. A particle can be in two places at once. Okay, textbooks state that the act of observing the particle collapses it. So don't observe them, because you're going to collapse the particles. You observe your table, it's going to collapse the wave function of the electron or the proton or whatever that makes up the table. And I suppose that your table collapses or disappears, I don't know, such that it appears at random in only one of its two locations. So it's at two locations or many locations. When you look at it, now it goes to one location because you looked at it. This is the nonsense that comes out of mathematical physics. A particle is made to be both here and there. These are the statements that these people make. And you might say, well, Bill, you don't have to take it literally. Should I? I mean, I thought physics was literal. I mean, you can use an analogy. You can say, my table is as hard as a tree. We can all understand that. But when you say that, a particle, when you look at it, it appears, it comes from all its locations and suddenly collapses into a point. This wave function, whatever a wave function is, it's spread out throughout the entire universe. And just because you look at the table, that wave function collapses to a point, to the atom, the electron, the proton, whatever, neutron, and that becomes something that you can see or touch or measure or whatever. Meaning that they put the observer at the center of all their theories. That's dangerous because that's opinionated. That means they're not going to have something objective out there. They say, well, it's not objective until you see it. Until then, it's subjective. It's flying around, it's vibrating, it's doing whatever. It's everywhere and nowhere. And then when you look at it, boom, comes all together into a point. Man, that's some magic. Okay, and but here you have. Not that I'm pulling out of nowhere here. You have New Scientist says the same thing. Antimatter is seen in two places at once, thanks to quantum experiment. A particle can be in two places at once, even if it is made of antimatter. Researchers have just performed an antimatter twist on a classical experiment used to show one of the foundational tenets of quantum mechanics, that all particles are also waves. Okay, so you have this notion that quantum mechanics has that a particle and a wave, that a light is both a particle and a wave, and an electron is both a particle and a wave. That way they cover all the bases. It's here and it's everywhere. It's both, here and everywhere. And it's only when you look at it that the wave collapses to a particle, and when you turn around, the particle goes back to being a wave. So, a particle can be in many places at once because they don't have a particle at that point. They have a wave, and it's a radial wave? It spreads throughout the whole universe. So it's not in one direction, it's everywhere, which contradicts the notion of the electromagnetic wave, the transverse wave. When they show you that, they don't show it going everywhere, like radially, like spherically. What they show is going in a single direction along an axis, and it vibrates or goes up and down or whatever along that axis. So we have these contradictions. That's why they can't illustrate what they're talking about. They simply cannot. It's impossible for them to do so. And you would say, well, that's a subatomic world. We can't see it. We don't know what's underneath. No. They've extrapolated this notion now to a bunch of atoms. They had to find jobs for all these people. And so they say, what do we do? Well, look to see if the wave function functions for many atoms. And so they have this. The same atoms exist in two places nearly 2 feet apart simultaneously. They're talking about atoms with S, okay? Quantum mechanics boasts all sorts of delightful odd features. There's a phenomenon called quantum superposition, okay? This principle of quantum mechanics suggests that particles can exist in two separate locations at once, okay? So I didn't invent this stuff, okay? Physicists from Stanford University? I didn't know they had physicists over there. Okay, have now demonstrated the superposition of a group of atoms. Now it's just one atom or a subatomic particle. Now we're talking about a group of atoms over a greater distance than ever before. And so they have them separated by more length than they had in the past, of more distance. Quantum superposition is made even more perplexing by the fact that it can only occur when the particles are unobserved. So please don't observe the particles, because then you won't see superposition. You got to, maybe, I don't know, I'm saying, what if we bring a blind man? Would that work? I mean, the guy's staring, but he can't see anything. Do you really have to see, or? I don't know. Okay, but forget about atoms. Now let's go into molecules. So, it's not only, they're getting bigger and bigger. Pretty soon your whole table is going to disappear as soon as you observe it. Okay, so it says giant molecules exist in two places at once in unprecedented quantum experiment. Giant molecules can be in two places at once thanks to quantum physics. Well, thank God, Every particle or group of particles in the universe is also a wave. Waves occupy multiple places in space at once, so any chunk of matter can also occupy two places at once. Okay, so that means your table can occupy two places at once, because now they're talking about chunks of matter. Groups of atoms. We're not talking about a little subatomic particle. We're talking about molecules here, guys. Physicists call this phenomenon quantum superposition, and for decades they have demonstrated it using small particles. Okay, so now they've demonstrated, they proved it, right? But in recent years, physicists have scaled up their experiments demonstrating quantum superposition using larger and larger particles. Now, in a paper published, blah, 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 okay, an international team of researchers has caused molecules made up to 2,000 atoms to occupy two places at the same time. So now we're talking about lots of atoms, okay? Now we're not talking about just a subatomic particle here, okay? They're saying if we have a bunch of atoms, molecules, right? Because 2,000 atoms, now you're talking a lot of stuff here. Now you're talking about stuff that could be visible maybe by a scanning electron microscope or atomic force microscope or one of those. But forget about little atoms, forget about little molecules. Let's talk about objects. Here we have large objects, okay? Okay? Need to be in two places at once? It may be possible. Quantum physics has demonstrated that tiny particles can exist in multiple places at once, but a new method may prove that it is possible for larger, visible objects to also exist in multiple places. Now we have Schrodinger's cat at two places, one alive, the other one dead. Quantum superposition, the quantum effect where particles exist concurrently in multiple places, has, historically speaking, only been thought to apply to tiny subatomic particles. But superposition of larger visible objects may in fact be possible. And so they have a paper there that they reference that proves it, that shows that it is within the possibilities. Yeah, pretty soon they're going to say your desk is at two places at once, okay? That's where they're headed, because this just keeps going on and on. At first it was subatomic particles. Now it's the whole your desk or your cat or whatever, your tree is a wave function, and as long as you're not looking at it, it's waving out there, throughout the whole universe. And when you turn around and look at it, now it collapses to a tree back again. Hopefully nobody looks at the trees that I got out there, because I need them all, because if I hope nobody watches them, because if they in the country it's said the other way around. I hope they watch them, because otherwise they're spread out throughout the universe. All the apples, everything's out throughout the universe. Many apples. Okay, but here we have you heard of Brian Greene, and he's got a different take on this. He says that it's not totally true that a particle can be at two places at once. That's the rabble version. That's for the masses, for the plebes out there. He's saying that really objects don't even have location to begin with. Electrons don't have location until you look at them. So he's got a different version of this. It's not that it's a wave function that is vibrating throughout the universe. It's that there is nothing there, and only when you look, that's when the electron suddenly collapses or appears. I don't know, I guess it's the wave function appearing, but he doesn't talk about wave function. He says the electron doesn't have location. That's what he says. So let's listen to good old Brian Greene here. Let's see what he has to say. Here it goes. Listen carefully to him.
The more precise way of thinking about quantum mechanics is there's simply no notion of the electron having a location, of occupying a position before you actually measure it.
So, what do you think? Now the electron doesn't have location. It's an object that exists but doesn't have location. And I thought that's what exist means, that it's an object that has location. So if it doesn't have location, it doesn't exist. And so I guess all the electrons that are making my camera here, my desk, etc., they don't have location until I look at them and suddenly they condense into an electron. I hope that's not the case with protons as well, because that would be protons, electrons, that's an atom. That means the atoms don't exist, don't have location until I look at them. That means my desk doesn't have location until I look at it. I'll let you figure all that out by yourself, okay? I mean, it's all total nonsense. These so-called explanations, physical interpretations, these mechanisms that quantum mechanics offers are total poppycock. Let's call it what it is. It's garbage, okay? That's what it is. Okay, here we have another fellow. His name is Lawrence Kraut, and he's going to tell us something about spin. And the funny part here is that, he says that some of these particles, like electrons, and maybe others as well, they spin in all directions simultaneously. Particles can spin in all different directions at the same time. I cannot even imagine that. I cannot imagine a particle in two places at once. Now they're saying that your top spins in a gazillion different directions at the same time. What sense does that make? And yeah, you won't hear from me. Okay, let's make sure we get it from a so-called mathematical physicist. Here we have Larry Kraut.
Let's say I take two electrons and I create states where one is spin up and one is spin down. Actually, they have opposite spins. It turns out they're spinning in all directions at the same time.
It turns out they're spinning in all directions at the same time.
Is that possible? That your top spins in all directions at the same time? And I guess it was proven by these two fellows. His name is Niels Bohr and Wolfgang Pauli. And here they were looking at a top. And I guess that's how they proved it. The top is spinning in gazillion directions at the same time. Okay, so maybe that's where Larry Krauss got it from. Okay, and do we stop there? No, we have now this thing called entanglement. And this is what Einstein called action at a distance, meaning that there's this remote control effect where you press your button on your remote control and the TV turns on, and there's nothing between your remote control and the TV. Now we know that's nonsense. We know that there's something there. Okay, imagine if you were out in space, right? And you have a remote control that doesn't work, doesn't have any light. In fact, you don't have to go to outer space. Just break your remote control, point it at your TV, and see if you can turn it on. It doesn't work. So there was something there that was turning on the TV. Once you break your remote control, you can't turn your TV on anymore. So obviously something is coming out of there, because otherwise your TV wouldn't turn on. Okay, so let's hear Larry again. He talks about entanglement. He gives you a brief introduction of what they proven. They always prove in quantum mechanics. So here it is. Listen carefully.
So it is true, and this bothered Einstein, this spooky action at a distance. It is true that I can do what's called entanglement. I can entangle two particles like two electrons or two photons, creating them in a very special quantum mechanical state. Now I measure this one, and I find out it's spinning over here. It immediately makes this one spin that way. Immediately. It's instantaneous.
So it's not only that one object affects another one, but it does it instantaneously, he says, whatever he means by instantaneous. I guess he's saying zero time, and zero time is instantaneous, but that's just location. That's a static concept. It's in a single frame of the Universal movie. And so who knows what they mean by instantaneous? They would have to define that word very precisely in order to make their case. But, so we have action at a distance, voodoo, magic, witchcraft, whatever you want to call it. And we also have the fact that it's instantaneous. Okay, so keep those two in mind. Okay, and finally we have this many copies of you running around. Doesn't that sound irrational to you, the fact that there's another you somewhere out there in the universe right now? They say there's so much matter out there, so many atoms, that there's got to be another Earth, and within that Earth, there's got to be another you, because there may be gazillions of Earths out there, and in one of them, we're going to find at least in one of them, we're going to find another you. This is kind of like previous lives, the fact that you come back to life after you die. It's kind of like that, because they're saying that there's two 2 U's somewhere out there in the universe. Maybe more than 2 U's, because they can stretch it out to say there's a gazillion U's. I never met another me. In fact, God forbid, you know. Okay, so this is what it looks like more or less. This is how they illustrate it. All these Earths out there. So that's the many worlds interpretation of quantum mechanics. Okay, that you know, something happens here, but it branches out into all these different worlds. Okay, and it's more or less like the multiverse that you're gonna hear about in general relativity. That there are many worlds out there, and really the only reason they invented the many worlds and the multiverse and all this kind of stuff, alternative realities and whatnot, is so that they don't answer the question. They just leave it. They leave it with the question unanswered. You say, what happened here? You know, and they say, well, in this world, in our world, in this Earth, right, in this part of the universe, you bought the lottery and you won you won the lottery, right? And the other one, someone killed you, and the other one, you robbed the bank, and so the next step is not guaranteed. You know, that way they keep, you know, your options open. There's no determinism. You know, you have this free will. And in this one, you use your free will to rob a bank. Here, you used it to win the lottery. Here, you used it to shovel, you know, snow off your lawn. So that way they keep their options open. They say they cannot predict what's going to happen next, you know, and the way they do it with these many worlds. And so these are just irrational explanations because they cannot answer the question. That's what it is. And so they created these nonsense explanations, if you can call them explanations, all irrational.